Okay, well, it is my honor and pleasure to introduce Jay McClelland tonight to you. Jay is officially a psychologist. He's been chair of the department at Stanford, but you might think of him as a computer scientist or a philosopher or a linguist or a cognitive scientist, because in fact, he's one of the rare people who is an expert in all of those fields. I've long admired Jay. He and his one-time collaborator, Dave Rumelhart, wrote what is still considered the Bible of connectionism or parallel distributed processing, or what has now become deep learning. The book is full of incredible examples that are still used in every course on connectionism or neural networks. He's done an amazing amount of work, and we'll get to hear some of his latest research today. But it's also worth pointing out that Jay is a devoted father and husband. He's got 2 daughters, and he and his wife have been married a very long time. He's won every award in the book, including the Rumelhart Prize in Cognitive Science, the Heineken Prize. He's a fellow of the National Science Foundation, and the National Academy of Sciences. I have no doubt. I don't see it, but I will assume. I don't want to waste his time with further introduction. I'm sure you know who he is as long as you're remotely connected to cognitive science. Jay, it's all yours.
Okay, thank you, Adele. And I'm going to share my screen. Hopefully you can all hear me and see the screen. So today I'm going to talk about the idea that we should think about language as being part of an integrated understanding system. And I'm going to just try to motivate this with a few ideas, findings, things that go back 50 years, really. But to just start with the basic point that I'd like to ground the whole talk in, which is that the main role of language is to support communication of information about situations. So what do I mean by a situation? Well, a situation is a set of relationships between real or fictitious objects and events as construed in the common ground between speakers and hearers. So here are a couple of sentences about situations. 3 turtles rested on a floating log and a fish swam under them. That's a situation. You can visualize it, I think. I certainly think of it like this, you know. There's a fish going underneath. The next sentence describes another situation. 3 turtles rested beside a floating log and a fish swam under them. So now I have the log and the fish is over here. So each of these 2 sentences has communicated a situation, obviously one that was made up and maybe has never happened, but which we can understand as though it happened, and we could read it in the newspaper, and it could be something that really happened or something like that. So this is what I mean when I say that language is about communication of information about situations. What a writer does is he writes something that tells someone about a situation, and what the listener does, the reader does, is form a representation in their mind of the situation that's been described in the language. Here's another example. Sorry, I should have mentioned that those sentences come from the work of John Bransford, who was very influential in the field of cognitive science in the 70s, in bringing forward the idea that language wasn't just about processing sentences and forming structural descriptions, it was about forming representations of situations. Here's another situation. John tried to put his trombone in his suitcase, but it was too small. When we read a sentence like this, we have a question which we could consider a linguistics question, which is, what is the referent of the pronoun it? You know, in a syntactic approach, we would ask the question whether it's the trombone or the suitcase, and think of these things maybe in terms of syntactic bindings. But in fact, in the underlying event, there's a suitcase, there's a trombone, and there's a process of fitting the trombone or trying to get it into it and realizing that it's not going to fit. And in order to resolve this, Winograd suggested we had to actually think about the trombone in the suitcase. Most approaches to language at the time weren't addressing this issue. So I'm just sort of channeling people who were arguing for this point of view 50 years ago. But I want to sort of get out on the table that situations can be extremely rich and complicated. Even a single sentence can communicate a very complicated set of interrelationships having to do with changes and beliefs over time about objects, not really objects, but categories of objects. So in some sense, a category is kind of an object. The giant sequoia, it's not a particular tree, it's a type of tree, right? So types can be objects. And so let's just read this sentence together. Botanists once believed that the coast redwood and the giant sequoia belonged to the same genus, but evidence from DNA sequencing has led to a reconsideration of this view. So this is a very complicated set of a situation involving relationships between other situations, like are these two things situated under the same node in some kind of imagined cognitive hierarchy or construed genealogical hierarchy, or are they in different places within that hierarchy? And I hope this brings out this notion of the construal and the common ground, so we understand that there are these taxonomies and things need to be placed within them and so on. So this is for me, this is what language is. It's a tool for communicating information about situations. So a considerable amount of research has gone into this kind of question about constructing situation representations. And the people who've done this kind of work have argued that, in fact, it generally involves the integration of information from multiple sources. There's the language itself. I give you a couple of sentences. But the language, requires you to make reference to things that you know, and to make bridging inferences that connect various things with each other. If I say John spread jam on some bread, the knife had been dipped in poison. Well, we link the knife to the spreading event as possible instrument of that action. That's a situation. And we think about the fact that if it had been dipped in poison, it might put the poison on the bread. We might then think of the person picking up the bread and biting into it and realize that they might become sick or even die just from eating this bread from this tiny little story. So we bring all of our knowledge to bear on this as we construct these situations. They're not, it's not the case that all aspects of them are actually described in the language we're given. The inferences are always required to bridge. So Bransford, among others, and others, part of his work was very influential in this, argued that we understand and remember texts better when we can relate them to a familiar situation. And at this point, I'm going to actually read you a little story that Bransford and his collaborator Johnson used in their study on this. I can get it to be big enough so I can read it here. Here's the little story. If the balloons pop, the sound wouldn't be able to carry since everything would be too far away from the correct floor. A closed window would also prevent the sound from carrying, since most buildings tend to be well insulated. Since the whole operation depends on a steady flow of electricity, a break in the middle of the wire would also cause problems. Well, that's not the whole story, but the rest of it goes on in a similar vein, and you're probably profoundly confused. But what Bransford and Johnson did was they showed some of the participants this picture to look at while they were hearing the story. And if they had seen this picture, then they would remember this story much better, and it would make sense to them. I guess in that order, right? It would make sense to them, and they would remember it better. So what we remember is this representation of the situation that the picture and the language help us construct. Now, in fact, we can, of course, build representations of situations without language at all. We can watch a silent movie. In this case, silence might not be the whole story, but even then, there's Romeo singing to Juliet on the balcony, and I think I remember Charlie Chaplin doing something like that in a totally silent movie, right? And so we can communicate information about all aspects of situations with all kinds of different kinds of information. So what we remember is the situation, not the details of the text. Of course, we can memorize text. We can get into the sound of the language itself. But a few minutes after hearing the first of the sentences below, people accept either of these two variants equally as having been the one that they'd heard, okay? 3 fish rested on a floating log and the fish swam under it, or 3 turtles rested on a floating log and a fish swam under them. Well, it's the same event because it and them are kind of like coordinated in that case. And so it sounds like what you retained, and you endorse it as having been what you previously experienced. So this is the fundamental point, is that language communicates about situations. Many sources of information can be used to construct representations of situations. And so language is then just one of the parts of this idea of an integrated understanding system. Last little point about this, just to maybe illustrate its immediacy a little further, is if you present a subject with a sentence, you're presenting it over headphones, so they're listening as it unfolds. The man drank, and they're looking at the picture that you see here. their eyes go to the empty beer glass. If the sentence says the woman will drink, this sentence goes to the wine glass. The eyes go to the wine glass. So the visual information and the language together mutually kind of shape our expectations and our understanding in real time and make it so that we actually even, other research has shown, sort of know what is going to come next, right? It's going to be the beer glass or the wine glass before it actually occurs, because we're doing these inferences slightly ahead of the point of the language. So I'm now going to get to a question that has been is sort of considered very central, and it's a question about compositionality of language. And we can ask the question, well, why is language compositional? And one idea is that this is an important fundamental aspect of linguistic representation. Okay. But I'm going to suggest that, in fact, the reason why language is compositional is that situations are compositional. So, for example, we could have this notion of someone picking an apple and giving it to someone. It could be all kinds of different people. They could fill that role. They could pick all kinds of different things. I mentioned an apple, but maybe a pear or an avocado, or they could do something other than pick an apple. They could buy a book or rent a movie, and then they can give it to someone, right? So there are these aspects of situations that recur in a way that confers a certain sort of compositionality on the situations, and which therefore might be ultimately the source of the compositionality of language, or even the idea that sentences express propositions about some entity and some other set of entities, right? So S goes to NP VP, where VP equals V plus parens NPs is perhaps just a basic residue of the fact that events happen to be, situations and events happen to be things that involve specifying a relationship between a number of entities. And so the entities themselves, of course, are distinct things, right? The world is populated by people and apples and other people, or books and objects, right? There's people and inanimate objects and beliefs and all kinds of other sort of abstract things out there that we talk about because they exist as things that we need to talk about in situations. And so I'm actually, somebody who is hugely sad that generative semantics died out. And I kind of think that, oh gosh, whenever I'm speaking, I'm trying to, from that point of view at least, I'm trying to generate a sentence from a semantic intention of communicating something to you about a situation. There's also a certain kind of, systematicity or compactness about this, right? The world, an event typically is affecting only a small portion of the universe. Now, the Big Bang, of course, affected the entire universe, but when John picks the apple from a tree, it's relatively encapsulated. There's a relatively small number of things that are affected, and so the idea that our sentences like pick out those things and foreground them for us is an important part of thinking about why it is that sentences are these discrete things that just pick out a small number of things. So if it were John and he picked an apple and gave it to Mary, then we know something about the participants involved in the action that occurred in this instance, and it captures most of the relevant participants and their relationships. Now, I say most because this is something that I think is important and often neglected. And it's hugely important to linguists, but it may not be, for me as a psychologist, it's completely inseparable from language itself. And that is that there's always a penumbra, right? There's always that knife that you use to spread peanut butter in the bread with. There's always the fact that the apple was in a branch, and when you pulled on the apple, it shook the branch, and it might have even caused another apple to fall. Or it might be that, you know, Mary's boyfriend is watching and he gets jealous. We could decide, of course, to mention these things, but as we understand, our understanding must sort of at least be ready to encompass these possible extensions that are associated with and sort of in the penumbra of the situation that's actually been described. And so that's another point that I'm going to stress, which is that compositionality is not universal or absolute, and it is best to think of it as a matter of degree. Okay. Oh. A couple more points and then I'm going to stop and see if there are any comments or questions. Language, we can gain experience about situations before we have language. I think animals gain a lot of information about situations and represent them. But language allows us to learn things about situations we've not witnessed, aspects we cannot observe, like, oh, somebody put a poison pill in that glass. Somebody could tell us that, and then we wouldn't want to drink from it. We could have witnessed them doing that, but language could tell us that. Or language could tell us about things that are harder to observe and that are tied in with social contracts, like ownership or creation. John made that. That's Bill's apple, you know. Of course, language informs us about all the construals that we place on things. So these taxonomic hierarchies I was describing before is a construal that arose from engagement among people who were trying to understand the organization of objects, of the plants and animals in their environment, and then became scientists about that. Language also informs us about properties that we might not even have thought about without having had a culture in which these properties had become important. So the society, culture creates properties and entities that we attend to, such as exact number. We know that Amazonians deep in the jungle of Brazil lack a concept of exact number, but in some cultures, exact number is so important that it is something that we represent about situations automatically. So I think language is profoundly important in shaping our representations of situations, but it's still about the situations. An exact number isn't a linguistic concept. It's a conceptual concept, and a taxonomic hierarchy similarly. Okay. In a nutshell, Language is not a distinct mental faculty. It is part of a system that we use to shape our representations of situations. Languages differ in the way that they do this. That makes one language different from another. And there may be some commonalities between languages and some of the ways they do it and some differences. And studying language per se is obviously interesting and important, but languages don't exist just to be themselves. They exist for this purpose. And okay, yes, so this is where I'm going to see if there are any comments, fierce arguments, decisions to abandon the talk now, or anything else. Adele, anybody raise anything about this?
People are shy so far, but maybe I'll ask you a question that I think the linguists in the audience would, are maybe thinking about, which is, so not every part of a sentence is equally substitutable. The agent argument is often the most substitutable. So, it's rare to find, if you can put John in the subject, you can put Mary in the subject, you can put Keisha in the subject, or he or she, and that seems to be true across languages. Whereas, so the subject is separate from the verb phrase, which is often more of a unit. Do you relate that to your idea of situations?
Yeah, actually I do. So very interesting you should ask that particular question, because in some work I did actually in the 1980s using neural networks inspired by Bransford's work and other people's work, I had this idea that was related to everything that I've actually been saying to you, in which I said, okay, well, so I want to build an understanding system. What is the understanding system going to do? It's going to take a sequence of words in, and what it's going to do is it's going to build a representation that allows it to specify the roles and the concepts that fill that role that have been described by the sentence. And in order to set up the training environment for my neural network, I said, okay, well, there's a set of events that could occur in the world. And one sort of set of events is eating events. People eat things. Another set of events is hitting events. They hit things like balls or other people, maybe. And another set of events is kissing events. They kiss other people. And in each of these cases, the verb kissing, eating, is sort of played a very central role in the sort of characterization of the event type, which then sort of specifies properties of the fillers of the various roles. And it was interesting. So all people eat, right? But they might eat different things. And so in our schemas, if somebody ate soup and they did it with daintiness, they were probably going to turn out to be maybe a woman, maybe a school teacher. Whereas if they ate steak with gusto, they were probably going to be a man, maybe a bus driver or a construction worker, something like that. So of course, this involves certain stereotypes that we may or may not want to reify in our models, but which sort of capture the ways in which there are dependencies, of course, in all aspects of these roles and these fillers. But yeah, so that's my way of thinking about this. The event schemas are the sources of the constraints, and the role constraints are sort of subsidiary to those, and the subject is a bit more free because of issues related to the event schemas and what they permit.
Yeah, that makes sense to me. There are a couple questions here. So Michael Plyer has asked, do you consider thought to be compositional as well as situations? And is that a different, would that be a different claim?
Well, I was trying to get to that point a little bit with the apple and the tree example, and I appreciate the question. I am going to argue soon that I want to think about thought as I think about everything else, including aspects of language itself, as quasi-compositional. And that's going to be why I'm going to argue for neural networks. So I'm going to, let's see what the other question is, and otherwise I can move on to the next part of the talk.
Great. No, it's related, I think. So Eli Matos says, if language is about situations, it can be represented schematically like frame semantics. So a la Fillmore, or is it possible that understanding language involves some kind of frame composition?
I think that that's a very useful approximate characterization of what understanding language involves.
Great.
And I'm going to get on with the business of talking about that pretty soon.
Okay.
Great. Okay, thanks. So what kind of computational system can capture human understanding of situations? Two perspectives. Abstraction, explicit representation of structure, and processing governed by structure-sensitive rules are inherent properties of the human understanding process. This is a perspective that is reflected, I think, in certainly Fodor and Polishin's article, which was offered as a knockdown destruction of the entire connectionist enterprise by Zenon and Jerry in 1988. And the alternative perspective that I'm going to offer is that abstraction, explicit representations of structure, sorry, there must be a typo in there, but everything else, I guess I should say, that you could stipulate, are useful approximate descriptive characterizations rather than properties of the actual computational systems underlying understanding. And I'm going to argue that human understanding arises from an underlyingly parallel distributed processing system implemented in the human brain, which can sometimes be usefully approximately characterized as adhering to constraints similar to the ones that Fodor and Polishin were arguing for. So why parallel distributed processing? A parallel distributed processing is the idea that there are all these little separate computational elements, like these neurons in the real brain, roughly 1 billion of them, or in our computer simulations, artificial neurons, or sometimes called units, that essentially each perform their own computation based on the influences they receive from other neurons. So that's the parallel part. All these little computations are going on simultaneously. These neurons influence each other through graded constraints. Each one's influence on another is a matter of degree. And these constraints can be mutual. That is to say, the neuron that's coding for one aspect of a situation could be mutually connected with the neuron that's coding for some other aspect of the situation. Maybe directly, maybe indirectly for another neuron somewhere. And these mutual constraints allow us to form an interpretation of input using information that may be noisy, incomplete, and or unreliable. Even if every aspect of an input is ambiguous, mutual constraint satisfaction can result in a coherent interpretation. And so if you take this kind of a perspective, you're always thinking of everything as being open to some degree of uncertainty. Like, you know, I use a particular word. Did I slip? Did I put the wrong word in there totally by accident? So that's one kind of uncertainty. Or the word may have multiple meanings. Am I referring to this giant sequoia or to the class of giant sequoias, right? The giant sequoia could be either one, depending on context. When we listen to actual speech transmitted to us via Zoom technology and our own input and output devices, we get noisy signals. And as we know, one of the first findings in psycholinguistics is that you hear the words that are being said much more clearly if the sentence makes sense to you than if it's a meaningless arrangement of words. George Miller was responsible for those very early and important findings. And so I'm not going to illustrate this with an example from language precisely because it's a very general principle. But this photograph that appeared in Life magazine, also about 50 years ago, I believe, kind of conveys this in a way that I think is very palpable. And that is that we can construct a representation of a situation from cues, none of which have any particular, definitive specificity. So it's not clear to me that everybody automatically sees this image here as what it actually is a photograph of. It was actually taken by a photographer, and then he pushed the image a little bit to make it appear the way it does. But probably most of you by now are beginning to see that there is a Dalmatian dog sniffing at the ground with its head right in the middle of the picture. And if you see that, you begin to see all kinds of other things. You see that this, can you see my mouse here? This arc is the dog's collar, and here's its nose sniffing at the ground, and oh gee, this must be its belly. And you can even kind of make out the shape of its leg back here, even though the cues for that are so vague and inconclusive. And so by using a parallel, by using neurons that are mutually constraining each other, we are able, this is the claim of PDP, we're able to construct a representation that captures all the, a lot about a situation using all of these partial and graded constraints, because when taken all together, they vote for one particular interpretation. So that is a very essential essence of the PDP approach. It's often lost in focuses on other questions like learning, but it's a central element and it plays a role in the rest of what I have to say. So I'm going to just sort of make sure that this point is clear. And in fact, this is where Rommel Hart and I started in our investigation of parallel distributed processing. He was actually interested in reading as an example of understanding. And he actually wrote a paper called An Interactive Model of Reading, in which he argued that all kinds of sources of information could mutually constrain each other as we read or as we understand speech. Both of those examples were referred to in the paper. And I teamed up with him around this particular issue, and we applied this idea to people's ability to use context to identify letters in words and pronounceable non-words. So that's David Rumelhart. And we explored what might happen when somebody sees a display like this and has to interpret what the word is and what the letter is that might be partially obscured by that little red blob that I've placed over it. And so we simply constructed a parallel distributed processing system consisting of neuron-like processing units for features of letters, for letters themselves, and then for words. And we connected them up with excitatory connections if they agreed with each other. So the letter T in the first position is consistent with the word time and vice versa. Those are mutually consistent. We allowed for inhibition among neurons that were mutually competitive alternatives for a particular aspect of the input, like all the different letters for the first position and so on were mutually inhibitory. And I just said those two things. And then we input the features that you see there, leaving out the ones that are obscured, and let the system settle. It's a gradual mutual constraint satisfaction process. So as the letters T and M and E are beginning to get activated, in the middle position, I and T are equally likely, but the word time gets supported by all of these other constraints, and then it feeds back and selects the I over the T and can feed back and fill in the missing features. So you imagine them behind the blob, if you like. So this model didn't learn, but it's inspired us to think about learning. Since letters and words are arbitrary and vary from language to language, we have to learn this stuff, right? Okay, so this is the first fundamental principle of parallel distributed processing, and it's going to be extremely important as we try to think about how people go about constructing situation representations, given the fact that the input is noisy, ambiguous, full of gaps and various things like that. But learning is also important. And here David was profoundly influential with collaboration with Jeff Hinton and Ron Williams. He figured out how to train multi-layered neural networks. This, this is the engine that's driving David's insight into how to do this, is the engine that drives all of deep learning. And there was this idea that we should start with a biological inspiration. This is actually a case where a computational inspiration was more important. Jeff Hinton said, wait a minute, you're trying to figure out how the brain solves a computational problem bottom up by thinking, what do neurons do? Let's start with how we might solve the problem from an optimization point of view. So we want to get this network to produce a particular desired output. How can we find the solution to that question? And so Dave started thinking about that after Jeff suggested that was the way to go, and he figured it out. And so now we have this algorithm that adjusts each connection to minimize the network's deviation from some desired output. And so the learning process is just driven by, we have inputs, we have our internal state, we may have internal state from before, we'll get to that in a second. We're now going to use it to predict what outputs we should observe, and when we see those outputs, they will help us drive learning. And this became the basis of subsequent work in the PDP framework, as well as almost all of deep learning. So I don't want to spend a lot of time on this. I got really excited about this. I'll just say that. I started applying this to reading, capturing the fact that people can read pronounceable nounwords, as well as real words, and seeing if we could capture that in a simple a neural network that mapped from orthography to phonology without any explicit rules, just using backprop to train it. And we trained it with words, but it generalized, the second iteration generalized actually in a human-like way to non-words. Produced some of the same errors that people made as well as the same correct responses. Actually, people's responses don't obey a system of rules. Instead, they reflect statistical patterns and similarity relationships. And that's why the model actually captured human data. It actually reflected those statistical relationships. We then applied this to semantic cognition, and this is where I started, I think, really connecting up with this ideas about situations and meaning and so on. I'm not going to go into this right now because I got 3 hours, right? You guys are all here for 3 hours. Now we're planning on wrapping up in well under 3 hours, but I do want to keep it a little bit more to the language side. So I'm going to skip over this, but the models showed in principle how aspects of language knowledge could be, this is the point that I will dwell on for a second, can be captured in a simple artificial neural network without building compositionality or structure sensitive rules in. Okay, so this is Jeff Ellman's really simple recurrent network shown here on the left. Okay, so now we've made a big step forward. And this is where the word distributed comes in, because we no longer have a unit for each item, like each letter or feature or word. We just have patterns of activation over collections of units that we discover, that we learn to form by using the backpropagation learning algorithm. So Ellman's network takes in a word, uses a set of connection weights to form an internal representation, and it takes its own representation that it had from the previous word with another set of connection weights, allowing that to shape the hidden representation as well. So I should have said it takes both the current word and the previous hidden representation through separate weight matrices to form the new hidden representation, which then predicts the output. And the crucial thing about this learning algorithm is that it not only learns the weights to go from the hidden representation to the output, but these other two matrices of weights as well. So that means it's learning weights for figuring out the implications of the current input, as well as weights for figuring out what I can use from the past to help me understand the current input. And the only thing that it's doing is predicting the next word. But it learns different representations for different words. These are distributed representations here on the slide. I've used red for relatively close to 0 values for units, and red for relatively close to 1, blue for relatively close to 0, and white for intermediate values. And you can see that the pattern for hit and the pattern for ball are quite different. Well, why are they different? Well, Jeff trained this model on sentences. And this model actually inspired that work I mentioned earlier that I did about situations, because each of these sentences actually described a little situation, like mice eat bread, monster chase cat. There were little event templates that were then filled in with the words that correspond to the agents that could occur in those event templates, but they were thought of as just sequences of words, right? And the network learned to predict the next word from these little training examples sentences that it received. And in so doing, it learned, and I'm not even showing you this because it was such a stark effect. The first thing it learned was how to separate the nouns from the verbs. The nouns and the verbs have completely different representations in this model. Why? Because the nouns, the verbs are followed by different things than nouns are. So if you're going to make correct predictions about the next word, you need to learn to treat the nouns and the verbs differently. I'm showing the subcategorization structure within the nouns to make the point that not only did the model capture the abstract, high-level categorical distinction between the nouns and the verb, but it also captured the subtler, lower-level distinctions that linguists can argue about as to whether they're in the grammar or in the semantics, right? So is animacy a feature of syntax or meaning? Well, ultimately, of course, it's a feature of meaning. And because sentences and actual events are all involve interactions between objects with these different types that have these importantly different properties, it's natural that sentences are going to reflect these regularities of the world. And so for me, this is the whole thing: nouns, verbs, animate, inanimate, human, animal, breakable, edible. All these distinctions are ultimately semantic ones. Okay, so that's a little bit of an aside, but rather than universal grammar, we have nouns and verbs emerging from a very, very simple statistical learning process. This guy should have won the Nobel Prize for that, right? So I've introduced two core principles here: multiple mutual constraint satisfaction, learn distributed representations that capture categorical and subcategorical information, and actually all the way down to the finest context-sensitive detail. And then the last point I'm going to make is, on this particular bit of work, is emergent structure sensitivity through connection-based learning. So this was Jeff's second paper about these things. He trained his network with sentences that now had embedded clauses in them, like this one. The boy who chased the dogs likes ice cream. And he asked the question whether, so not all the sentences had embedded clauses. Some of them did, some of them didn't. And the network is just learning to predict the next word as it goes along. And what he was able to show was that the network actually learned to establish the appropriate agreement between the matrix subject NP, the boy, and the verb likes, even when the embedded clause ends with a NP that's going to vote for a different number marker for the verb, right? So the boy who chased the dogs likes ice cream. It's not the dogs like ice cream. And so it's not about, the local adjacency relation would say, oh, you should pay attention to dogs, but you don't. The network learned to actually use the subject NP to determine whether the verb should be marked, the matrix subject, the main clause verb should be marked. So that was an example of emergent structure sensitivity through connection-based learning. This was published in 1991. So I'm going to now tell you this little unit of my thought about why it's good to use PDP models and not just write down a bunch of structure-sensitive rules. And my argument is that the reason has something to do with the fact that virtually all natural that is to say real objects, and linguistic entities, like words, and structures, are quasi-regular. They exhibit varying degrees of idiosyncrasy, coupled with varying degrees of consistency with broader patterns of typicality and regularity. Okay, so I'm giving you this little litany over many different types of entities that exhibit quasi-regularity. Okay, so let's take the past tense. The word biked is considered to be a completely regular past tense. It is something you can generate by applying the past tense rule, add ed, and then a small phonological conditioning rule to delete the and make the voicing of the dental stop consistent with the voicing of the preceding stop. So you say liked, biked. Liked is like that too, except that if you actually record somebody's speech when they say liked instead of biked, it turns out when they say biked, they articulate that aspiration of that agreeing T more strongly. When they say liked, they don't articulate it as much. It's a little bit less voiced. And even there's a little bit of irregularity sneaking in. But let's consider the next one on my list, slept. This is just like those other things. We spell it differently, right? So it's an exceptional spelling. But if you think about the pronunciation, it's just like biked and beeped. But except for the fact that we adjust the vowel a little bit, right? So we can use, if our neural network learns these regularities, the neural network can use the same knowledge about these regularities when it deals with slept as it uses when it deals with biked and liked. But it can also just sort of like tweak the whole thing a little bit so that it's using its knowledge of the typical pattern when it's dealing with the exception. And we never have to make a decision whether something's an exception or belongs to a different category or not. Okay, so let's consider a few other examples. Said, very similar, right? It's the past of say, but you reduce the vowel a little bit. Did, you altered the vowel a little bit more in this case, but it's like dude, right? Made, well, maked is a little bit cumbersome. In Old English, it was makode, but it got compressed down to made. Then there are things like swim and swam and went and was that, okay, maybe there's a few words that are really very much less regular, but languages only have like 2 or 3 words like was that has no sort of relation at all to the stem form of the word. And it's usually associated with the most frequent verb in the language. You guys would know how to describe that in linguistic terms better than I did. Even went is like a past tense, and then it ends with this, and it is the past tense of a word wend that dropped out and got bound to a different word instead. So in spelling and mapping from spelling to sound, we have all the same things again. Make is totally regular. Plead is regular, but there's a lot of exceptions around, or maybe there's EA is sort of sometimes, especially with D, is sometimes S, sometimes E, we don't know, it's sort of in between. Bread is on the other side of that boundary, it's bread instead of breed. Pint, the P and the N and the T are just completely regular, but the I, you've got to tweak that a little bit. So in our model that maps from spelling to sound, it uses the same knowledge when it produces pint that it uses when it produces mint and lint, but it just tweaks it a little bit to get the I right. Of course, and it often mispronounces it as pint, especially if it's a low frequency exception. If you're British, it's not a low frequency word, so you're gonna not make that mistake. These other ones are still quasi-regular, even less so, perhaps. So then let's take horses. Well, horses are very kind of typical four-legged animals. Okay, that's fine, but camels are, well, they're like horses, except they have a hump. And elephants oh, they got these trunks and these tusks and these big floppy ears. They're still a lot like four-legged animals, but they have these idiosyncratic properties. Penguins, what category do they belong? So it's, you get further up, but it's still got a lot of things that it shares with other biological kinds. So it's quasi-regular everywhere. Inflectional morphology has this character, and in fact, as Joan Bybee's work points out, you have a word like prefix. This is a very compositional word. It's pronounced in that compositional way. As you go down through this list, the words are pronounced less compositionally and their meanings are less and less compositional. So predict is not just to say before, it's to actually make a claim about a future outcome, right? And so that's not just compositional. There's something added there, but those constraints are useful, right? They help you with that, but they're not determinative in that way. And so mapping to meaning from morphemes is one of the places where you just can't imagine that for most morphology, it's going to work in a compositional way. And this is why Adele is one of my favorite scientists. She thinks about sentences like these and others. We have NP, V, NP, and we have a word like hit, which takes a concrete object as its object NP, and a animate agent or a something that has been put in motion by an animate agent, such as a rock or a bat, anyway, obviously not exactly that even then. It's then, oh, wait a minute, the particular NPs that might get used there, and then the meaning of the word hit becomes a little different when we change what that NP is. So the meaning of the verb is not itself completely compositional in this way. When you get to she felt the baby kick, this, maybe it's an English colloquialism, but this was something that a young lady once pointed out to me. It means this amazing event that a woman who has a new life growing in her womb has experienced for the first time, perhaps. An amazingly important event in the life of a human being. And we can get that out of reading this sentence if we're in the right context. And it can essentially mean that. Of course, it can mean the baby was running around on the floor and was kicking at all kinds of things, and she was lying on the floor sleeping, but then she felt the baby kick, and then he really did just kick her the way you might have ordinarily interpreted it. She kicked the bucket. So this gets towards the extreme end where there's less systematicity at all. But even here, you could say she will kick the bucket. She kicked the bucket good and hard. You can elaborate this in ways that make it not completely outside of the realm of engaging with more systematic aspects of language. So we always need to have the regular and the quasi-regular working simultaneously in all aspects of language processing and semantic interpretation of events and objects. So when processing quasi-regular items, neural networks employ their knowledge of what is typical while also capturing what makes an item an exception. To an extent, of course, that depends on how frequently they've encountered this information about the exception. And a really important part about this is we do not have to decide how to chop a continuum of examples into particular taxonomic types. We never have to decide what to put in the lexicon and what to put in the rule system. We just use graded connection-based learning. and it gets sorted out through the learning process. Well, that's why neural networks are so powerful. I'm going to move on at this point because I see we've gone past an hour already and only just begun. But so obviously this message didn't get through the first time. And it was probably because the models didn't scale up, or at least that must have been a part of it. Because, you know, Jeff Ellman's example about the agreement of the subject MP and the matrix subject with the matrix verb across an embedding was very hard to extend to larger training corpora. And, you know, there was no AI applications of any of this. And so, you know, it remained a fascination to those of us who were true believers and were trying to understand certain neuropsychological findings. But the models didn't scale up. And so, yeah, people were saying, well, you see, you need rules. You're not going to get anywhere unless you build in those damn rules. But then that all changed completely. We had AlexNet that is a deep neural network trained with backprop that does image classification and caused a huge drop in the error rate, sufficient to get everybody's attention. And that was a big breakthrough. We have DeepMind's deep Q learning systems that surpass human level performance on many Atari games. And we have, of course, AlphaGo and other amazing deep neural network applications that have surpassed human abilities in certain ways. I don't say in all ways, but in certain ways in games like chess and Go. And so we now live in a very different world. And, you know, there was this breakthrough article, there was this article in the New York Times Magazine in December of 2016. It's called The Great AI Awakening, which, you know, reflected this. And it was all about the neural machine translation system that came out of Google and was noticed by people who were typing things into Google Translate and getting garbage back. And all of a sudden the garbage was way better. So we're going to talk about this example for a couple of minutes, okay? So this was in the article in the New York Times. And I routinely give this to my class to look at and ask them to read both of these two things and see which they think is the original and which they think is a translation that was produced by going from the English to Japanese and then back to the English using the Google neural machine translation, which of course you have the possibility of loss and distortion in both directions. So I'll read them aloud so we both get a chance to grok them together. We all get a chance. Kilimanjaro is a mountain of 19,710 feet, covered with snow, and is said to be the highest mountain in Africa. The summit of the west is called Ngai Ngoi, and I don't know how to pronounce that, so apologies. In Maasai, the house of God. Near the top of the west, there is a dry and frozen dead body of a leopard. No one has ever explained what the leopard wanted at that altitude. Not bad. Now let's read the other one. Kilimanjaro is a snow-covered mountain, 19,710 feet high, and is said to be the highest mountain in Africa. Its western summit is called the Maasai Ngai Ngai, the house of God. Close to the western summit, there is the dried and frozen carcass of a leopard. No one has explained what the leopard was seeking at that altitude. I added two articles, two thes, into the bidirectional translation version to make it a little harder to tell the difference. And I don't claim that people can't tell the difference here. They can usually if they think about it. But it's amazingly good, I still think. And to answer the question, the second one is what Hemingway wrote. And it has some nuances and some subtler word choices that maybe give it away, like carcass as opposed to dead body and things of that kind. But it woke people up, led to a New York Times article, led me to decide I wanted to go and affiliate myself with people who are working on these kinds of problems because, well, fundamentally, I've been trying to argue that they're right about this for a very long time, and it was very exciting to me. So one of the things about the Google Neural Machine Translation System that was used for this work is that it's very deep. And they, it's a beautiful article because they discuss all the properties of this architecture and why they're important and relevant. And what they say about this property is that in our experiments, we found that for the neural machine translation systems to achieve a good accuracy, both the neural networks, encoder ones, the ones that are doing the English and the ones that are producing the Japanese, have to be deep enough to capture subtle irregularities in the source and target languages. And by that, I take them to mean dealing with all the regular structure while also capturing the quasi-regular elements. And so the argument here, and I don't think there's probably a knockdown proof of it, but one of the authors of this has argued this repeatedly, that it's a sort of the gradual translation from the input to the output that allows for the subtle manipulation of the way words are used in one language to capture how they should be used in another, such that you can actually get something that isn't completely brittle and it's going to fail. So in this kind of a system, both the knowledge is in the connection weights, right? It's learned stuff that is in the connections between the neurons, and the representation of a particular aspect of the input, like the pattern of activation somewhere in the network, is very difficult to pinpoint and make explicit. Somehow or other, it's distributed throughout the whole thing, such that the output is the right answer, but it's very hard to find. And this characteristic may be intrinsically related to the success of these networks. Okay, so this is the end of Roman numeral 2. So are there questions at this point, or?
There was one question from a little earlier, which was that Jerry Feldman proposed structured connectionism using PDP and engineering. In your opinion, why is this kind of connectionism, why didn't it receive more attention? Or I don't know if you're familiar with Jerry's structured connectionism. I don't think it was deep learning, but there was some engineering included, which in some ways is reminiscent of today's models. So this is Eli Matos who's asking.
Well, interestingly enough, I didn't know that Jerry Fodor had proposed.
Well, not Jerry Fodor, sorry, I might have misspoken. Jerry Feldman at ICSI.
Oh, right, thank you.
Sorry.
I wasn't hurt. I do know about him.
Yeah.
Yeah, so it's very interesting. He was a very early connectionist. I remember we had workshops back in like 1980, right around the time the interactive activation model was just in press. And he had a paper called Connectionist Models. And his argument was there weren't enough time steps. So, for all of the sequential processes that standard symbol processing systems do. So we're gonna build structured models, but they do it in a small number of time steps, like a few feed-forward iterations through neurons could do. That was his main argument. Well, I think the problem is that you just can't build the right units and connections from explicit representations of linguistic regularities that you have extracted by analyzing languages to capture the subtle nuances. It hasn't worked. Of course, far be it from me to say that it can't work, but what I've been trying to argue is that when you build it in, it kind of forces you into a Procrustean bed, and you're stuck with the inferences that the rules you thought of are going to make rather than the ones that emerge from the statistics. And when you think about, so that paper I mentioned before on this slide here is not only about gradients, but it's also about change. That word liked, it gets more and more compressed, and eventually the K is going to drop out of it. It's going to be like, and sometimes actually it is pronounced that way already. And then when people come around later and they write it down the way that they're hearing it now, they're going to start spelling it without the K in it. Why is that? Because these things are continuous. There is no discrete symbol anywhere in the system, and the discrete rules aren't going to work with them. All right, so we get to capture language change as well. Okay, so now I'm about to enter the third phase of the talk. And I see that we've already gone for 1 hour and 17-ish minutes. And so, yeah, I'll figure to try to go for another 15 or 20 minutes, and then we'll take a general discussion. I will probably still have some uncompleted material even then, but we'll see. Okay, so now I want you to think about this problem, and I'm going to give you a little text to process with me. It's a little story about John, who put some beer in a cooler and went out with his friends to play volleyball. Soon after he left, someone took the beer out of the cooler. And in fact, the story goes on for a while. You could imagine that it's a very heated match, and the different teams are playing against each other back and forth. And, the other team is up by 3-1, but John's team wins the next 3 games in a row, and they come home victorious. So John and his friends were thirsty after the game. They went back to his place for some beers. When John opened the cooler, he discovered that the beer was gone. Well, you should have predicted that, although you may be processing the talk at a meta level and not the level of the actual content of the example. So you may have missed that. But if, people do, in fact, show evidence of making these predictions, even from just a single occurrence of this word in the earlier context. And this has been, this was a very serious problem for the Google GNMT back in 2016, although they were beginning to tap into what has turned out to be the solution. And I'm now going to tell you a little bit about, some of the solutions to that and how I think they should be tweaked to capture the way the human mind might solve these particular problems. Okay, but here's the basic problem. You need to be able to use information that occurred a long time in the past, sort of an indefinite time in the past, in order to make the appropriate predictions. And I tried to illustrate that by throwing in sort of an arbitrary amount of intermediate text in that little story. And if you use this architecture, which is essentially Jeff Ellman's architecture on steroids, it still has this property that information you have about things that occurred in the past, so you imagine a sequence of words coming in at the bottom, and you're trying to predict the next one out at the top, and you want this prediction for word, 173 to depend somehow on word 4 in the text, you're forcing it to go through the same bottleneck that all the other information has to go through. And eventually it's a lossy system. It's not going to be able to preserve all that information. So although there were some very fancy and elegant bells and whistles that were added to these things that made these systems do as well as they did for a while, it didn't turn out to really solve the problem as well as needed. And those of you who know much about neural networks probably know this, but there was a very, very important breakthrough that was an important reason why these language models are now doing as well as they are. And that is a mechanism that is called query-based attention. Now, I'm telling you about this because it's going to link back to some of those ideas from the very beginning of the talk about constraint satisfaction. But you can already see why this is relevant, right? Because the context that has some of the constraint could be indefinitely far back in the past. But here's the basic idea. I get a word, bad, that occurs after having processed some contexts. And in this case, I have this simple context. John hit the ball with the, and now we have the word bat. So the word bat, of course, could be a little flying animal, or it could be the instrument that we use to hit a ball, or possibly some other things. And we need to know which of those it is to make future predictions effectively. And so we're going to, and we also need to often query information in the context just to know how to predict the very next word effectively. And so what we're going to do is we're going to formulate a query. So the neural network essentially has a set of connection weights that are used to form a representation, which is called a query. And then for each of the words that occurred in the past, you essentially compare this query to some representation of the word. So we have representations of all the words that occurred in the past. It could be 170. In some cases, it's up to like almost 4,000 words in the past. We can compare it to all of them. This is parallel. And in the hardware, actually, that we now have allows this kind of parallelism, actually. And then for each of those, we get back a similarity, which is essentially how similar are these two. And then we assign a weight so that the most similar one gets the greatest weight. That happens to be hit here. So this guy agrees quite a bit with hit. It's sort of, I think of it as looking for a verb that might tell me what kind of a bat I am. If it was fly, then, but maybe this sort of part of the pattern here is sort of like a verb-like part. Okay, ask what kind of verb, that's what we're going to get back. So the weight is going to then be multiplied times this vector and all the other weights times the other vectors. We get the scaled vectors, we add them all up, and this is now our answer to the question. It may tell us what kind of a bat this is because we were able to query anything in this indefinitely long context. Okay, that overcomes this bottleneck problem because everything is there subject to a query equally. So this is a version of this. It's called Transformer XL. This is a very reduced sketch of it, but the idea is that you have 24 layers deep. This only shows, essentially the input layer doesn't count. So this is like 3 layers deep, but imagine another 21. And at each layer, you look back over a window. You might look back over about 150 segments for each one. So by the time you stack up all these layers, the direct and indirect paths look back over 3,800 segments, and you have the potential for taking 3,800 segments worth of context into account. So that allows these networks to exploit context in a far more open-ended way than they ever could before, and has been an important part of their success. But what really got me excited about this was mutual constraint satisfaction versions of these. And I'm just going to remind you of mutual constraint satisfaction by asking you to just read these sentences. So hopefully you're reading them. The first one says, Jack and Jill went up the hill. The second one says, the pole vault was the last event. But actually, the word went in the first and the word event in the second are actually the very same bit of handwriting. It's actually Rummelhart's handwriting. This is his example. That was cut and pasted into both sentences. It's cut from one, pasted in the other. And, you know, we seamlessly interpret this as one word in one context and another word in the other context, using all these constraints in turn, including our knowledge about Jack and Jill going up hills, and, you know, verbs following noun phrases, and last being a good predictor of the event, and so on. BERT is essentially a mutual constraint satisfaction model. In that same sense, it allows all aspects of the context to be used simultaneously to constrain all other aspects. So all words are constraining each other at the same time. So here's how it works. You've got a set of slots on the input for different segments of the input. Usually they're word length, but if they're very long words, they have to get broken up. But anyway, this is an example from actually the blog post about this, the precursor of this model. We want to interpret the bank of the river. And of course, the word bank here is the ambiguity. And we want to imagine that we get to use all aspects of the context so that when we come to translate it, the representation we have of bank is already appropriate. You know, it's a financial, it's the side of the river rather than a financial institution. So we would use, if we were translating into French, we'd use a different word for it. The way it works is that at each position, a query is formulated. Those are the little red boxes here, but we're focusing on bank. And then at each position, there's a representation called a key, which is compared to that query. And you get that weighting, which you then use to multiply times all of the value vectors, which are the parts of the information about the word that you're going to return. So you get query-based attention over all elements of the context, and that then conditions your prediction of this word. And you do it simultaneously for all words at the same time. So they're all mutually constraining each other. This goes on through, I forget, usually 12-ish layers. And they actually train it to do filling in gaps that are left in the input. They leave a word out of the input, or they put a word in there that isn't the right one, and you have to correct it. And that's how they train this model. It learns how to use the context in this bidirectional way. And that's been a major contributor to both my fascination by these models and also to the literature in deep learning. So really briefly, we need some sort of compromise between these two approaches. I believe that we do want to use a little bit of future context together with things we've built up from the past. And so I sort of, the way I imagine it, and there's data on this from human experiments that I could talk about if anybody's interested, we use a little bit of look ahead before we commit to an interpretation of a word, a little bit of this mutual constraint satisfaction, if you like, right around the place where we're currently reading. And then we also have the benefit of the prior context. And so sort of the idea that I have about this is that we have this sort of small amount of parallelism over a few segments, a few words, together with the ability to query information in memory. That's extends, in fact, indefinitely into the past. Okay. So I may not get to the last part of the talk, but I'm going to go a little further, and I'm going to motivate this by something that I did last night, which is to see how well Google Translate is doing at translating various sentences. And I decided to try this out in Portuguese for the sake of the fact that I'm speaking to a Portuguese audience, or some people, I guess, who speak Portuguese. Hopefully you all speak English, or else this has been a complete loss for you, right? But let's just take this sentence here. The hen that chased the dog was too shaggy. All right, so this is like Elman's sentence. Who's shaggy? It's not the dog, even though semantically you think of dogs as shaggy, right? But that's got to be the embedded clause, and it must be the hen that was shaggy, right? So I tried this out. I just said, translate this into Portuguese for me. And it agreed the gender of shaggy with the hen, okay? I don't really know Portuguese, but this is somewhat similar to the Spanish, so I figure it's probably about right. And it got the agreement right, okay? So it did fine. But I also tried it on this one, our Winograd sentence from before. The trombone did not fit in the suitcase because it was too small. And again, it's the suitcase that must be too small, right? Not the trombone, or at least that's what people will say. And in this case, it got it wrong. It agreed small with trombone. It's masculine, right? And I have repeatedly found this with almost any sentence. I've mostly been doing this with Spanish. Sometimes
Jay, the screen froze. Hmm. What?
Well, my computer crashed
Okay,
and I'm back, but
great.
yes, thanks for hanging in there, those of you who are still here.
Let's see.
So where was I? My
Uh,
slides crashed as well. I have to reboot them.
Okay, so you had just done the mutual constraint satisfaction, the Devlin with the red boxes, and then you had turned to the next slide.
Right. Okay, opening the slides here.
I
And,
will tell you the number. So there was a question while you're getting that.
okay.
Together,
Yeah,
was,
we talked about one. I'll bring up the slide and then I'll take the question.
okay.
Here we go. Share screen. Okay. Okay. Okay, yeah, so that's where I was.
Great, right.
And what was the question?
Oh, so the question was about the last slide was, so a second language speaker said that they didn't get the event. They kept reading went. And I wonder if that's because maybe the pole vault and the last didn't constrain their network enough for the threshold of event to be matched. This is
Yeah,
the
where did that slide go? Yeah.
the handwriting.
And
Or
yeah.
if the context includes the previous sentence, right, then
you have another source of constraint, obviously.
yeah.
And I don't mean to say that these things always come out one way or the other. Of course, there may have been others in the audience who were not fooled. But most of my co-authors thought this was a cool thing to put into our paper when I first shared it with them. So, yeah, it's going to be a matter of degree. And one of the things that we know about actual second language reading, which is very interesting, is that you do have a kind of a tunnel vision in second language reading. You have to pay so much attention to decoding each individual segment that you haven't got much left over for the context. So that could be a part of the explanation.
Mm-hmm.
We could obviously take a vote of how many people were fooled, but that's not, super important. It's just the idea that you kind of acknowledge that you can be fooled, right? That's important here. So back to the to this issue here. And this is the broader question that I think many people are thinking and working on now, who are interested in these deep learning models, and that we wrote about essentially in our article, which is the idea that there is a lot of information about events in language, as I've noted several times. So it's possible to learn a lot about events just from language. On the other hand, it may be that some of the inductive biases that we bring to the language learning task come from the fact that usually when we get to language, we've had a lot of experience in the world. We have experience witnessing events, and we've had participating in events by using our own bodies to interact with physical objects in the world and with other people in the world. And mommy comes over when we cry if we're a tiny baby, these are all different sources of information that obviously are part of what we have at our disposal when it comes to beginning to learn about language, and part of what we rely on in real time as we process language. I already emphasized that. So this led me to propose in this paper that appeared last year in the Proceedings of the National Academy of Sciences, a model of the human understanding system, which I consider to be a model of understanding events, which can use language as well as other sources of information, including visual information, to provide information about events. And then we talked about the actual organization of this system in the brain. But let me just talk about the basic idea here. So one part of it is the notion that there's an object representation system, very heavily tied to vision, but not exclusively. And it's involved in, what we see about objects when we look at them, as well as other sources of information we have about them, such as the sounds that they make, or the actions that they undergo, which of course may come to us through vision, or what they smell like, what happens when we throw a ball to them, what happens when we pick them up, what we feel in our hands. But just for the sake of simplicity, we're going to imagine we have the visual and the auditory sources of information about that. And at the same time, we might have language that co-occurs with this. So if we have, we're watching, a baseball game and the announcer says the bat hit the ball or the bat hit, we would anticipate the ball in part because of what we're seeing, but in part because we know there's a baseball player there from the visual input. So these are mutual constraining sources of information go into constructing our representation of this event. This is also taking place within a spatiotemporal context. And so what I envision is that this spatiotemporal context is kind of like a kind of a higher level distributed representation that characterizes the global aspects of the situation, in which this little micro situation of a boy hitting the ball with the bat is taking place. And the idea is that these are all mutually interacting systems with bidirectional connections between them, so that they can all work together in a mutual constraint satisfaction process, allowing what you see to be constrained by the language and the context, and allowing what you hear to be constrained by the objects and the context, and of course allowing the context to be constrained by prior context and the objects in the language together. And that this system is very much like sort of an extension that we might make of these language systems, but with the idea that while they're processing a language in one channel, they're also processing movies or streams of images in another channel. And that we're using this BERT-style query-based attention both within the object and the language and between them, so that the queries from the objects can go and ask questions of the language, and the queries from the language can go and ask questions of the objects, and they can also both ask questions of the context. And of course, the context can ask questions of them. And so working together using query-based attention as an extension of the initial sort of basic interactive activation framework for mutual constraint satisfaction, we have a potentially extremely powerful model of the understanding system in the human brain. Now, this idea about unlimited context playing a role is one that is addressed in this model by a brain system, or a simulation of a brain system, which we know about from the effects of brain damage on memory. And I'll first tell you about the proposal here, which is that there's a separate system, which we're going to think of as a memory, in which we essentially store the patterns that are constructed in these various modules in the rest of the system. And they can all be there. And this is thought of as like a computer memory, in the sense that it has no hard boundary on the number of items that we can store. We could always buy another disk or another bunch of RAM and plug it in, and our address space at least can encompass all of this, right? And the reason why this is somewhat justified by the effects, by what we know about humans, is that there is a part of the brain called the medial temporal lobe, which, if you remove it, results in an inability to learn new things quickly or to access specific information that was experienced recently prior to the brain damage. But it leaves you with the ability to, for example, do most of the things we've talked about up to now, like, except remembering that ice that had been taken out of the cooler. You wouldn't remember that because that was too far back. But the immediate local context, amnesics can exploit that just like normal people do. And they can understand and engage in conversation with you over a very short stretch of time. If you talk to them for too long, they start going back to previous topics of conversation because they can't remember that they talked about them. Or if you go out of the room and come back, they may think that they've never met you before because they aren't retaining any permanent record of anything. They only have essentially this immediate context state to work with. And the way we deal with the indefinite memory problem is that we have this other system that's mutually connected to the rest of the system, which is sort of thought of as being embedded in the rest of the brain. Okay, so I'm pretty much at the end. I was going to say a little bit more about the particular brain areas involved in each of these different systems and some of the evidence for the idea that they are, in fact, somewhat separable parts of different brain areas. I'll just mention one of these. And this was something I found myself pondering quite a bit was as we wrote the article. It's very clear that there's this object system. I guess I'm mentioning two. I'm going to talk about the object one and the language one briefly. Because there's a part of the brain which, if it's degraded, if it's affected by neurodegenerative disease or damage on both sides of the brain by brain injury, the patient will no longer be able to name concrete objects or link the sounds that objects make with the pictures of the objects, or to tell you whether a pyramid goes better with some palm trees or some pine trees, whether shown with words or with pictures. Okay, so it's not purely linguistic. You can access it from language, you can access it from pictures, and it seems to be about objects and their interrelationships. Those patients lose the ability to name concrete objects. On the other hand, if you have damage to another part of the system, you become disfluent. You can't produce small syntactic words like articles or prepositions. And many people used to think about it as being particularly syntactic in nature, but it turns out that verbs are also affected, and other kinds of abstract words are also affected. And so it's sort of as though there's kind of an sense in which the kind of the meaning of relational language, including prepositions, right, is tied up with, after all, prepositions are actually specifying spatial relationships, not just syntactic relationships. That is subserved sort of jointly, by language. So it's sort of more like objects and relations almost. I almost wanted to call that language module the relation module. Now, of course, for me, everything is sort of quasi, and so, one word rather than another is always a Procrustean bed that I'm foisting onto something, but that's the kind of an interesting aspect of the literature on this. And in case you're sort of interested, this is a very crude, rough sketch of some of the brain systems and their locations in the brain that are associated with these different components. So I'm going to wrap up. Not so much with this slide, because I sort of hinted at most of this, but by pointing at some additional challenges and opportunities that I'm not going to talk about, but which are obviously important. So, as envisioned here, I thought of it as integrating other modalities and the consequences of one's own and others' actions as additional sources of information about situations. These are extremely important and relevant to sort of like causal attributions, I think, and many other people, of course, are pursuing those ideas. Building systems that understand abstract situations and relations is, of course, much more heavily tied with language, and the actual physical grounding is, of course, much more tenuous in those cases. But we do have the work of Lakoff and others sort of pointing towards how often these abstractions are built on metaphorical extensions of very concrete relations and concrete language. And although I don't take that as far as Lakoff does, I think that they do provide a scaffolding which is going to turn out to be an important inductive bias as we try to build systems that understand more abstract systems, but that's a very speculative future direction. I think one of the things that's profoundly missing from all these models is goals and a sense of purpose. When I read an article in the literature, at least, or something about the status of travel restrictions, I'm reading for a purpose. I want to know if I'm going to be able to go to Europe this summer or not, and so there's certain parts of the input that I'm encoding, and I'm, my goals as a comprehender are important. And of course, the listener has to understand the goals of the speaker too. And so having representations of self's goals and others' goals, we've got to have that in here. I totally accept all that. And that's an extension way beyond anything currently that I understand on the table. Or, yeah, so actually, I sort of contradicting myself here. Some of these kinds of issues about goals and purpose have been raised by other deep learning literatures. I do think that they're more remote in terms of actual successes, but things are moving in the direction of thinking about all of these kinds of things. And so just to leave you with the very simple kind of fundamental punchline of all of this, language is for me a part of an integrated understanding system that depends on mutual constraint satisfaction and graded distributed representations to succeed. And I'll stop there.
Okay, well, thank you so much. We'll give you a virtual round of applause. I know you can't hear the YouTube audience. So while people are thinking about questions, can I ask one?
Sure.
So this is a wonderful talk and a tour through so many of the topics that are interesting to me. It occurs to me, though, that the context itself needs to be quasi-regular with irregular pockets, right? Where, the context of a science fiction movie is going to suspend certain things, or the context of you speaking versus someone else speaking will create a subtly different context in much the same way that language does, but less rigidly, right? Where, so I wonder if anyone's tackling that instead of, ultimately it can't be a fixed, 170 previous slots for context. It has to be a hierarchy of contexts of some sort, like we have in language.
Yeah. So, just to refer to this diagram when I talk about this, I do think that there's some recursion-like features to how this all works that are going to turn out to be necessary. In other words, when we think about objects, it already comes up, right? An automobile consists of a whole bunch of parts organized into a coherent whole with a bunch of relationships. And of course, if we look at the wheel, there's the tire on the wheel, and then there's the hub, and then there's the bolts that attach that to the rest of the car. And we can sort of, treat the wheel as the context and the individual bolt as the object, or we can treat the car as the context and the wheel as the object, or we can treat the car as just one car on a great big car transport truck that's got 6 or 8 cars on it, right? And we have to be able to sort of swap around what's the context and what's the object. And so that's maybe a fundamental sense in which some sort of recursion-like property of that's what recursion gives you. You totally switch your context from the matrix clause to the embedded clause or something like that, right? And that's one of the things I always thought was like important about that, about how to think about language. But of course, it's extremely hard to say which is the object and which is the context too sometimes, right? Famous poems that have these kinds of things in them by famous poets. And so I think it's really important to sort of acknowledge that while also really acknowledging that there must be in some sense a kind of a hierarchy there as well, which I totally agree with. Now, yeah. And of course in movies or we can do this, right? Alice could take the pill and we could zoom down to a small size, and then she could take the other one and suddenly she gets larger. And in our imagination, we do these kinds of transformations all the time. But some of the evidence that goes into supporting this theory, so you know, is that if somebody is watching a episode of a television serial like the Sherlock episode that played on, there was a BBC thing and it was on Masterpiece Theater in the US, but it was used in a neuroscience study of these things. When the scene shifts, Sherlock comes into an apartment with Watson. They look around in the apartment for a while, frustratedly, and then Sherlock says, aha, and runs out of the room again. There's like, okay, something happened there. There's this big brainwave and then there's a context switch, and the context representation suddenly changes radically. And people are now able to track these context representations using multivoxel pattern analysis, which is essentially the same idea as these distributed representations that we've been talking about, right? And so the brain uses these distributed representations, and that's how we track brain states, and that's how we understand the representations the brain is using for these things. And I think of course, they're fuzzy enough that they're never, precise because of the noise in the recording, but I think that they will also turn out to be, very quasi-regular, as you suggest, if we could look at them in even more gory detail.
Nice, yeah. Yeah, that's interesting work. There's some of that going on at Princeton.
Indeed, that's where it is. That's where it happened. Yeah.
Okay, yeah. So there's a question from Michael Pliers asking if you could touch briefly upon the role of quasi-compositionality in the system.
The quasi-compositionality is a description that I use to characterize the fuzziness of the boundaries that arise when we think about these kinds of things. They come up in relation to the question about whether an argument is an obligatory or an optional argument, right? So the core of some verb argument structure is something that has a couple of obligatory arguments, like it requires a direct object and an optional indirect object or something like that. But there's going to be matters of degree on that, and the roles themselves, I've always thought, my God, this is a perfect opportunity for, like I was talking about that question about what the subcategory was of the subject NP in the hit sentence. And I was suddenly reminded of, the rock rolled down the hill and crushed the cottage in the village. And I'm thinking, okay, sort of, hit, it could also, the bat flew out of the player's hands and hit a person in the stands, and the bat hits, the player hits, there's sort of a quasi-agency involved in that, but more so when it's the player than the bat. But I always struggled with that one, right? Which role am I putting these things in? Well, you can put either in the subject position. You know much more about that than I do, I'm sure, Tal. And so, it's sort of like all of the roles are kind of like And that was one of the main purposes of that work I was telling you about that I did all those years ago. You know, what role are we going to say this particular prepositional phrase plays? He ate the spaghetti with a fork. He ate it with meatballs. He ate it with his friends. Those are very different roles, and you know, we got to use our knowledge about these sort of graded sort of acceptance constraints that situations place on fillers and kinds of roles that those fillers might play in order to capture that. So
fair, yeah.
That addresses the question.
Okay, so there's lots of clapping and lots of compliments on the talk. And Tiago Torrent is asking if you could elaborate a bit more on the sources that a language models might use in order to address the issue of meaning construal or goals and purposes.
Well,
or would you have to think about the notion of meaning differently, he's asking.
Well, I mean, I think that's a great question. So I don't consider myself an expert on those kinds of things. I have colleagues here at Stanford who I consider to have given these issues far more thought than I have, and I am going to defer to others in this regard to a huge extent. I will just say that you know, we can have a little discourse about the Sally Ann experiment where, you know, the one child sees two objects or an object's placed in a box and then goes out of the room, and another child is still in the room and observes somebody take the object out of the box, and the box is closed again, and the other child comes back in the room, and you ask the one who's been in the room the whole time, does she think the object's in the box or not? If the child is young enough, they get it wrong, right? They think that the other child knows what they know. If they're a little older, they have built up a representation of the situation that includes the knowledge and beliefs that the other party has. So I'm not entirely sure that it ultimately is any different from any other kind of complex situation that we might encounter. It does involve other people and the contents of their minds. But I sometimes wonder whether, I guess I think that all the same issues come up in other settings as well. And I think it'll be, yeah, those are my thoughts about that.
Yeah. Yeah, that makes sense. It seems like another case where the narrowing of the context or some subcontext, like a recursive embedding is needed.
Yeah, and you know, sometimes reminds me of another sort of kind of global point that I'm making in a piece of work with one of my current students, which is that in a sense, we do need to have the hierarchy of contexts in mind as we're kind of engaged in the sub-activities within a embedded sort of context, right? So we can always think, okay, when I'm planning my trip to London, you know, there's the first question about which airline and what date and, you know, which class of travel I'm going to go in, book my ticket. And then when it's time to, you know, go to the airport, I decide on a mode of transportation to get to the airport. And you could think of these as quite unrelated, right? I mean, it doesn't matter whether I take a cab or, the super shuttle or drive my own car, except that, oh my God, if the plane leaves at 11:39 and it's already 10:15 and it's an international flight, I better the hell take my own car and park it at the very expensive parking lot, or else I'm going to miss the plane, right? So I've got to have that the global situation in mind to some extent as I choose the instrumental pieces of the immediate proximal task. And so I think, that's one of the things about a strict sort of subroutine calling that I resist, and it makes it so that it's got to be sort of softer kind of, and that's what's afforded by these attention-like mechanisms that don't rigidly decide to, okay, now we're doing a subroutine call and then we switched context completely and now we've come back, and so it'll turn out to be really interesting to follow how that all shakes out as people and I try to pursue how to get these things to appropriately constrain their behavior by context while still being open to all of the constraints that they need to be open to. I think that's the fundamental tension that I've always felt.
Right, right. All right, well, I think we may have demanded enough of your time, but a lot of compliments here. Great talk, thanks so much. Yeah, so I'll thank the audience for tuning in, and yeah, thanks for another wonderful Aberlin talk. Jay, it was great to hear this.
Thank you, Adele. Thanks for your questions.